Hi, I'm Alex Giladi. I'm a fellow at Comcast and I'm leading the Advanced Technologies group in Viper Architecture here in Comcast. So this talk is about minimizing the manifest overhead and it's heavily dash specific. Let's first look at a normal streaming session, what it looks like and where does the overhead live. Let's say we have a football game, we have a camera at the stadium. Then we go and send a feed to the multi-rate encoder. The multi-rate encoder generates multiple bit rates, multiple representations in dash terminology. All of this then goes to the packager. The packager generates discrete segments and a manifest MPD in dash terminology. MPD contains all the information you need to both select the representations you want and issue HTTP GET for each segment you want to bring. So from the streaming client standpoint, the streaming client issues an HTTP GET, gets an MPD, parses it. Having parsed the MPD, it discovers what are the representations, what are the segments it wants to fetch. It issues HTTP GET requests for segments, and in many cases the next thing it will do is fetch MPD, parse it again, and figure out the next segments again, and so on. So this immediately brings us to the issue of a manifest overhead. Let's define it first. So the most visible aspect here is the bandwidth taken by the MPD downloads. Secondly, we have the number of HTTP GET requests that are needed in order to download these MPDs, and this translates into CDN load. Now, the next two things are slightly more parser and client oriented. First of all, we have a startup delay because we need to both download the MPD and parse it. And then we have the processing overhead of parsing the MPD and doing operations on it, and memory overhead of actually keeping the whole thing in memory. Now, is this an issue? The typical answer people give is no. But if you actually measure it, it is a significant issue for linear and DVR services. The reason is that with features like advertisement, with multi-DRM, with segment losses, you can get to pretty significant sizes of MPDs, and then with the 2-second duration of a segment in dash, which is a fairly typical deployment, and client logic that requests MPD every segment, you end up with 1800 MPD requests per hour. And if you do that, this is again a pretty significant number. So let's see whether we can reduce the manifest overhead and how much of a problem it is. So we managed to get to more than 2 megabits in a pathologic case, 2 megabits worth of MPD traffic. Just to visualize it, this is what it costs you to go and provide HD using HEVC. Now we managed to go and get it down to below 2 kilobits, which is arguably a pretty decent result. Now on the request rate reduction front, we discussed 1800 requests per hour, but with some ingenuity we can go and get to about a dozen. Let's see how we can do this. So first of all, we'll go and discuss reducing the traffic overhead, and there are 3 methods we're going to talk about. HTTP compression, which is a generic method, and then 2 dash specific methods, MPD patches, and asynchronous MPD updates. The next thing we'll talk about is how to reduce the footprint in terms of memory and processing. Let's start with on-the-wire compression. So this is something that is simple and also does not depend on dash. It is a functionality of HTTP.1.1. What you do is you just compress the body of HTTP response with a known algorithm, and the known algorithms are firstly gzip and deflate. They are pretty classic compression algorithms, and their support is mandated by HTTP 1.1. Then there is a newer and better performing algorithm. Broadly, it's not required by HTTP 1.1. It's supported, and it is an IETF standard. So if you look at a table here, you'll see that broadly performs amazingly well and significantly better than gzip on especially larger MPDs, where it is able to attack the issue of very high redundancy of the document. Now, we just discussed the issue of compressing in an application-agnostic way. So there is a bad side to it. We're completely ignoring the application aspects, and let's go and try doing something that is dash specific. Let's look at the sequence of MPDs as opposed to looking at given documents. The difference between two consecutive MPDs in the vast majority of cases is going to be minimal. Let's say you added one segment and you may have removed one segment. If you have one adaptation set for audio and one adaptation set for video, the whole difference is 4 lines. Now, we've seen that the worst case of an MPD size is actually half a meg. Now, why the heck would you go and download half a meg when you only need 4 lines? So this is exactly what people thought when they introduced MPD patches. So the original patch was very similar to the Unix diff utility, and 3GPP invented it and intended to operate on MPD as a file. Unfortunately, it doesn't work that well on XML, and later versions switched from line-oriented to XPath-based patching. So you are basically going and addressing discrete elements or attributes within the MPD. We have 3 directives: add, remove, replace. So the blue part of the patch example here shows the actual patching. How do we add new segments? And then the red part is some amount of housekeeping. Your typical diff can be actually applied to a slightly different version of the code. Here, we never ever want to apply something to a different base MPD, because it will work, and it will also create a situation where you may be in an inconsistent state. So we're checking whether the MPD is the correct MPD and whether its version is the correct version, and at the end of the patching we increment the MPD version. Now let's see how it actually works in terms of performance. So as you may have noticed, patches are tiny. So we actually need less than 1 kilobyte for one video and one audio adaptation set. And it's also less than 10 XML elements, and you may have hundreds of them in a full MPD, if not thousands. Now, this takes care of the memory and processing overhead. Now, they also compress well, and if you look at the actual numbers, the performance improvement is fairly amazing. We start with a naive approach. Again, let's take the extreme, 2157 kilobits. If we go and just do compression, we get to 43 kilobits. If we don't do compression and just do patching, we get to 4 kilobits, which is, again, a pretty decent improvement. If we go and combine the two tools and use compressed patches, we're at 1.55 kilobits, and it is a pretty stable number here. So it's probably a pretty decent improvement from 2 megabits to less than 2 kilobits. Now, why would we do anything else? And here is the reason. Patches, what we've done was we reduced the traffic, and we still have the same 1800 HTTP GET requests, but just in the majority of cases, the response fits into one Ethernet frame. Now, what can we do to go and reduce the actual request frequency? We can use the dash templates in a predictive way. So, what is a template? A template is just a glorified printf. You say that your segment URLs look like segment and then some number. And then you say, let's start with the number 1, let's end with the number 99, and just expand this one-liner to segment 1.mp4, segment 2.mp4, and all the way till segment 99.mp4. And in Dash, you can have two things. One is just an incrementing segment number, as in this example, or more interestingly, time, which is the presentation time of the first frame in the segment. Now, in both cases, the consequence is you can predict the segment URL before you actually go and get it. Since you can do this, ideally, you can go and download your MPD only once in the beginning of time, and then download a segment, look at its duration, construct the next request given the duration and the template, and you're done. And you can keep doing this forever. This is called timeline extension, and this is described in -IFIOP. There is a problem with this. The turkey problem. A turkey is being fed by a butcher, and it's fed pretty regularly. It knows when it will be fed. It can even build pretty graphs about it. But then we have Thanksgiving. So here, what if there is an ad? What if there is a new period? What if we lost a segment? In all these cases, you'll either get a 404, or you can get a segment that you cannot decode, and then, given the error, you'll need to go and download the MPD, and then you'll figure out what to do next. Unfortunately, this is not what we want to have in something that is a live channel, and again, as in everything in Dash, you have a tool for that. MPD validity expiration event is what helps you here. So this is an EMSG, an in-band event, a blob of data embedded into the beginning of a media segment. What it does is it tells the client, hey, your MPD is going to become invalid at time X. Please go and download a new one. So if you go and issue this event every time when there will be a material change to the MPD, let's say a new period, you can go and trigger a request for the MPD. So you are always running with the most current MPD, but you are still guessing the next URL. Let's see how it works. And the short answer, again, very efficiently. If you look at the number of GET requests, and let's assume that we have roughly 12 periods an hour, we can go and get from 1800 to 12 requests. And then, in terms of traffic, we're also pretty efficient. So without compression, we get from 2157 to 14 kilobits. If we do compression, we actually get to about 300 bits per second, which again is a pretty impressive result. I think with these results, we probably exhausted our possibilities in terms of reducing the traffic, but we haven't done anything to address the footprint, with the exception of what we've done with MPD patches. Now, if we want to go and reduce the footprint and reduce the parsing, we need a couple of things. First of all, we really want to be concise, and a couple of things there. You never want to put a segment timeline at representation level. I actually never thought that I need to do a slide on this, but I've seen vendors do this, unfortunately. Overall, anything that pertains to all representations should only appear at adaptation set level. And an example here beyond segment timeline is in-band event stream. You, by definition, have the same EMSG at the beginning of all aligned segments within the adaptation set. Why would you announce this multiple times? Another thing, please mind the default values. If you have an attribute that has a default value and it takes this default value, it's already known. You don't need to go and say this again. An example is scan type. Scan type is progressive by default. Please don't use it in your MPD unless you're actually dealing with interlaced content, which is arguably fairly unlikely. Last recommendation, use short namespace prefix when you are using external namespaces such as SCT35, play ready, and so on. Now, for something completely different, a couple of dash tools that help you stay concise. First of all, gap signaling. What is a gap? Segments can be lost due to transcode ratio, due to transcoder input failure, or due to network failure. What you'll actually get, imagine that you have a representation that is 720p, that is 540p, and so on. Let's say you have 5 representations like this. And then the 720p representation lost one segment. All of a sudden, if you interpret this naively, you have a period that has 5 representations, then you lose one, you have 4 representations, you need to cut a period, then the representation that lost a segment recovered, then all of a sudden you have again 5 representations and you create a new period. All of this because of one single failure. And we've actually observed more than 100 periods on misbehaving feeds. This becomes also problematic for players because you end up with very short periods of a few seconds. Now, the solution of multiple periods is unfortunately insane. And in order to avoid it, we can go and signal these gaps explicitly in the MPD. There is an element introduced in the 4th edition of the spec, failover content. You put it on the representation level, and what it says is you don't have any segments between time x and time y for this representation. In addition to making things more functional, it also reduces the number of XML elements you need to express the same thing, and it's pretty drastic from, let's say, 126 in an example we worked with, down from 365. And then it also reduces the size. We can do something that is 62 kilobytes instead of something that is 184. In both cases, it's a pretty decent improvement in terms of footprint. The last tool we're going to talk about today is content protection referencing. Why do we care? Unfortunately, when you have multiple DRMs, DRM information can take about 70% of the MPD in your worst case. Why? Because for every single adaptation set, you need to signal whether it is encrypted. It is done by a content protection descriptor for every DRM that you are using. Now, as an optimization that is very, very common and is also recommended by the HIF, you include your license acquisition information, typically the content of your PSSH box, in this element. Now, typically, again, it's exactly the same for the same period, and it's exactly the same for all periods in many linear cases. However, you need to put it into each adaptation set at each period. So we ended up, for instance, with 72 identical copies of a PSSH in a 9-period MPD. So this is where the 70% comes from. Now the solution is very simple, and it was recently added to the upcoming 5th edition of Dash. You just create another 73rd descriptor, which is the only one that contains a copy of PSSH. The rest of the descriptors contain a reference by name to that descriptor. This again brings down your memory footprint pretty significantly. So let's say in case of a single period MPD, from 62 kilobytes to 18 kilobytes. As you can see, it does nothing in terms of compressing on the wire. The difference is only in the memory footprint. So over the last 19 minutes, we've discussed how traffic overheads can be reduced by more than 99.99%. And you can do this combining HTTP compression with either MPD patches or asynchronous MPD updates. Then we discussed how we can reduce a size of a discrete MPD. First of all, by just being concise and doing the right thing, and then by using several of the newer tools in Dash. Now, we've been talking about MPD. Can we do anything else that is lossless and as useful? I think that yes, we can. And there are still system headers that are highly redundant. Let's say movebox, non-VCL null units, things like closed captioning, which are mostly zeros. So we won't get 2 megabits out of it, but we still can get something out of it, especially in low latency and low rate representations. So I hope we can discuss the results there in Mile High Video 2021, hopefully in person. Thank you so much, and please try this either at home or in your Dash deployment. Thank you.